Hello students, welcome to the class. So today we will do the NCERT exercise of the chapter Thermodynamics. So there are total of 7 questions that we will cover today. So you can see them, the list of these questions. This is the disclaimer. Now, our objective would be to cover as much problem as we can. Now there is a part that I want to say. I have arranged the question in such a way that you can take a look at all the concepts given in your chapter, right? So I have arranged them in such way, and I would suggest you that you try to solve the remaining problem by yourself. If you have a problem, you can just visit our website and post it in the forum, or you can join the Zoom meeting as well. So, right. So this is the thing. Now let us begin with the first question. The question says that you have to see that the delta H naught value is to be compared with the delta U naught value, and it is already given. Delta U naught is given as minus X kilojoule per mole. Now this is for the reaction which is specifically combustion of methane. So there are 4 situations. Whether your enthalpy will be equals to the internal energy, will be greater than the internal energy, less than the internal energy, or equals to the 0. So your time to solve this question starts now. It's a simple one. You just have to go back to the concept of the relation between the delta H naught and delta U naught, and you will get your answer. First of all, try to write the equation and then try to compare the delta H naught and delta U naught. So your time starts now. Okay, so as I have told, just follow the algorithm that I have told you. Just start from writing the equation. Remember the relation between the enthalpy change and the internal energy change, and then you can easily get your answer. You have 5 more seconds to solve it. So your time is up. Let us look at the answer. So the answer would be less than delta U naught, which is third option. How we will solve it? First of all, write the equation for the combustion of methane. So it's very simple. Whenever you burn a hydrocarbon, you always get carbon dioxide and water. The only thing that is need to be done is the work of balancing, and it's the most important part. You can see that I have multiplied the oxygen with 2 to balance the oxygen molecule, right? Then on the right hand side, I have multiplied the water molecule with 2 as a coefficient, again to balance the hydrogens and oxygen. Now, if I look at the equation, what can I analyze? We can say that the number of gaseous reactants is 3, right? It's very clear that it is 3. 2 is coming from the oxygen molecule and 1 is coming from the methane. What about the product? So, if you look on the product side, we have only one gaseous species, which is carbon dioxide. The other one is water, which is again a liquid. So, we will not consider it as the gaseous product. If this is the value for the gaseous reactants and gaseous products, then we can calculate the change in number of gaseous molecules, delta Ng, which is 1 minus 3, and that will be equals to minus 2. So you got your change in number of gaseous molecules. Now coming back to the equation which relates your enthalpy change and the internal energy change. So that equation can be written as delta H naught is equals to delta U naught plus delta NGRT. So this is your equation. We have already calculated the delta Ng. We know the value of delta U. Let us put it in the equation. What we will get? We'll get our final equation, the enthalpy change as minus X minus 2RT. Now what you can say from this equation? You can say that delta H naught will be less than delta U naught. Why I am saying it? Because whatever value you get for the enthalpy change, the internal energy change, you have to decrease it by 2RT, and then you will get the value of enthalpy change. So it's very clear from the equation. So you will always get a lesser value for the enthalpy change as compared to the delta U naught, and it will be lessened by 2RT. And hence you are getting your answer as delta H naught is less than delta U naught. Now moving on to the next question, which is 5.5. The question says that you have the enthalpy of combustion for methane, graphite, and dihydrogen as 890.3 kilojoule per mole, then 393.5 kilojoule per mole, and 285.8 kilojoule per mole. So these are respectively for methane, graphite, and hydrogen. One thing more you can notice, and you know it very obvious, and it's an important point, that the combustion process always releases energy, and you can see it very clearly from the examples. They all have a negative value of the enthalpy change. Now, if you have this information, can you just rearrange the equations? You can apply the Hess's law of constant heat summation to get the enthalpy of formation for methane, right? You have 4 different values. Just try to calculate it. I would suggest you first write all the things that are given and write the thermochemical equation, right? Okay, so write the given data in terms of thermochemical equation, then just rearrange it to get your final equation, which is for formation of the methane. You know it very well for the formation of the methane. If you're writing it for the formation of methane, then in the thermochemical equation, you will take the reactants in the reference state, right? And the reference states of the element, each individual element. So this is the main part. So if you are able to just rearrange it and utilize or exploit the equations, you can easily get the answer for enthalpy of formation for methane. Your time starts now. At least come at the final equation. You don't have to bring out the final answer. If you are doing it, well and good. If you are not doing, at least come at the final equation and compare it with the solution that I would give you. That would be enough. You have 5 more seconds. So your time is up. Let's see. The correct answer would be the first one, which is minus 74.8 kilojoule per mole. How we will solve it? Now, in the question, we are given with the combustion of methane. Its value is minus 890.3 kilojoule per mole. Now, if you are talking about the combustion reaction, then what we will write for the thermochemical part? It's very simple. We will take 1 mole of methane, we'll burn it with the oxygen to give us carbon dioxide and water. Next thing you have to do is to balance the equation. Okay, you cannot change the methane's coefficient. It's very important to remember that you are not going to change the methane's coefficient at all, because for combustion you have to remember that the definition itself says that combustion is for the 1 mole, right? Now this value is given as minus 890.3 kilojoule per mole. You will write this in the way that I have written, because this is the thermochemical equation for the combustion of methane. Similarly, you can write it for the carbon. Now, if I ask you for what will be the case for carbon, then the answer would be you will get carbon dioxide. During the oxidation of the carbon solid, you will get carbon dioxide. And we will take the standard thing, which is graphite. And in this situation, we will get the energy released as 393.5 kilojoule per mole. Mark it as equation number 2. Now coming on to the last thing, which is combustion of hydrogen. Now combustion of hydrogen is also very simple. It will give you water. And remember, you will take 1 mole of what? Molecular of hydrogen, right? The same thing is applied for carbon, 1 mole of the carbon, and same thing is applied for the methane. The value for the dihydrogen combustion is given as 285.8 kilojoule per mole. So this much energy is released. Mark it as equation number 3. Now, if this is the given data and we are already aware about the target situation, then we can write the corresponding thermochemical equation. If you look at the thermochemical equation for the formation of methane, you can easily notice that we have taken the carbon and dihydrogen in their standard state, right? We have mentioned the states, which is solid and gas for the carbon and hydrogen respectively. For the methane, we have taken it as again gas. You can also see that we are forming 1 mole of methane and from its constituent element at standard state. So this is your target equation. Now you have to rearrange the equation 1, 2 and 3. How you would think it? What would be your mindset? See, in the final equation, if you see, you can see that the methane is on the right hand side. But there is only one equation that contains methane, and which is combustion of methane. But in that case, the methane is present on the left hand side. So one thing you can think for sure, you have to reverse this equation number 1 to get the methane on the right hand side. So that is for sure. Okay. So this can be your initial point. Now I am letting it up to you that you solve it for the further process. Meanwhile, I will move on to the next part of the solution. Okay, so if you are getting the point, you don't have to wait for me. Just start solving it by yourself. Once you get this visual representation of what we need and what is given, you may be able to predict the next path from my hint. Okay, so I have given a hint also that for methane you need to on the right hand side. So we will reverse the equation number 1. Okay. So if you continue with that situation, Then we would rearrange the equation, and the first thing that we will do is reversing the equation 1, as I said it in the previous part. Now in this situation, I am writing it as delta H2. Why I am writing it as delta H2? The thing is very simple, because now we are not dealing with the combustion of methane. It's a different equation. You can see that the methane is not being combusted. Instead of that, it is being produced. So I have taken a different enthalpy symbol, which is delta H2. And upon reversing the equation, what will happen? To the enthalpy change, it will also reverse its sign. So now we will have the enthalpy change for the given reaction, for the reversed reaction, I would say, it will be 890.3 kilojoule per mole with a positive sign. Mark it as equation number 4. The next thing that I will do is multiplying the equation by 2. Which one? Equation number 3. Now why I have multiplied it? You will get your answer when I will show you the 3 equations that we have got. I have nothing to do with the second equation. I have reversed the first equation and multiplied the third equation with 2. You will apply the same thing with the enthalpy change as well. And in the last part, we will simply add the equation number 2 as it is, 4 and 5. What will happen? So this is equation number 2, this is equation number 4, and this is your equation number 5. If you will add these 3, then the 2H2O and 2H2O will get cancelled out. See, these two things will get cancelled out in the 4th and 5th equation. So that is the reason I was multiplying the 5th equation by 2, because if you look at the last equation, which is formation of methane, we don't have any species like water. We have carbon and we have hydrogen, and then we have the methane. That's all. Molecular hydrogen, I would say, and then we have the methane. We don't have water molecular or anything like that. For that case, I am making sure that the water gets cancelled out, and as a result, I am multiplying the equation number 3 by 2. Now this same thing is being applied for the case of hydrogen. Why? Because if you look at the final equation, we need 4 atoms of methane, 4 atoms of hydrogen. But according to the equation, we have only 2 coming from the dihydrogen. So we multiplied the whole by 2 to get 4 hydrogen atoms. Got it? And also, we need to cancel out the oxygen. Right? You can see that we have oxygen here and we need to cancel it out. How it will cancel out? So on the reactant side, for the second and fifth equation, we have 2 molecular oxygen. So that will result into 2. And on the product side, if you look on the equation number 4, then we have 2 on the product side. Now this 3 terms will get cancelled out, and at last we will get our final equation, which is the formation of methane. You can just look at the equation, you are getting the same thing. Now in this case, I have not done anything with the enthalpy change. So I have done it intentionally so that you can see that what I am doing what I am doing with the enthalpy part. So 3 things we were doing. First is reversing the equation, second is multiplying the equation, one of the equation, and third thing is adding all of this. Now you can see the same in the final equation. See, we have multiplied it with the 2 for the combustion of hydrogen. Then for the methane, we have reversed it. So we have taken a negative sign. And at last, we have added these 3 terms to get it for the formation of methane. If you substitute the values, what you will get accordingly, you will get the final value for the combustion of methane as minus 74.8 kilojoule per mole. So this is your final answer. Is it clear to all of you? It's very simple, although it may look complicated at the first sight, but just try to solve it by yourself on your notebook. It's very easy. Take 3 to 4 examples. From those 4 examples, you will easily get the concept for any question similar to this type. Okay. So if this is clear, we can move further. Here is the next question. A reaction A plus B is giving us C plus D along with some heat, which is represented as Q. Now you have to decide that the reaction will be possible at high temperature. So basically you have to decide the spontaneity. So if it is spontaneous as high temperature or at low temperature or at any temperature, or it is not possible at any temperature. So these are the 4 situations which are mentioned. Your time to think about it starts now. I am giving you a hint here. Here you have to check for the spontaneity. So where you will go? You will go towards the Gibbs free energy change, which is delta H minus delta Ts. Now you can get your answer, I hope. You have 15 more seconds. Think about it. Okay, your time is up. The correct answer will be that the reaction will be possible at all temperatures or at any temperature. How do we come at this situation? For that, you have to look at the equation. It says that Q amount of heat is released, right? It is written well in the question also. And the second thing that is mentioned is your inotropy change is positive. Now, if I start from the first information, which is plus Q, then what we can say that since your heat is released on the reaction, therefore your reaction is exothermic. Okay, so this will be very true. As the heat is released, so the reaction will be exothermic in nature. That means your delta H is negative. Next is for the inotropy. Now it is already given in a very clear word that your inotropy is positive. Inotropy changes positive. Therefore, delta S will be greater than 0. Now, if delta H is less than 0 and delta S is greater than 0, then we can finally put this situation in the final equation of Gibbs free energy. What is that final equation for the Gibbs free energy? It is written as delta G is equals to delta H minus T delta S. If your delta H is less than 0, see here, listen it very carefully. If your delta H is less than 0, that means this whole term is equals to less than 0. Sorry, this whole term will be less than 0. And if delta S is less than 0, and we know that temperature can never be negative, it is very difficult to reach, or if I would say it is hypothetical till date. So this T delta S will be positive as a whole, but along with the negative sign, this whole thing will turn into a negative part. So delta H is negative and this right side thing is also negative. So what we can say that if both of the situations are telling it as negative, then the sum will be always negative. Suppose you are taking minus 2 and minus 3. Yeah, what you will get an answer? Minus 5. You can take any term along with a negative sign, add both of them, you will always get a negative sum. So it's for sure. Therefore, your delta G will be negative for the given situation at all temperature, no matter how high or how low temperature you are considering. Therefore, the reaction will be spontaneous at any temperature. Is it clear to all of you? It's very simple. Just analyze both of the given information and you will get your answer. Okay, now there may be confusion at some point that this Q is not equals to delta H. But if you are saying that Q is given out, right? Q is given out during the reaction, although delta H may not be equal to Q, but the thing is for sure that the reaction will be exothermic. If the Q is negative, the reaction will be exothermic. So that is for sure. Moving on to the next question. Now it's a very important one. Okay, so there are several concepts involved in it. Just listen to this question very carefully. Question says that the enthalpy change on freezing of 1 mole, I would say the per mole of water at 10 degrees Celsius to ice at 10 minus 10 degrees Celsius will be what? The delta H fusion is mentioned. It is plus 6.03 kilojoule per mole. So obviously it will be positive because energy is required to break, or I would say melt a given solid into liquid. And this thing will happen at 0 degrees Celsius, of course, because water is your situation. Now, along with this, two must informations are given, which is heat capacity at constant pressure for the liquid water, 75.3 kilojoule, joule per mole per Kelvin. And then we have the heat capacity for the water in the solid state as well, which is 36.8. Now your time to solve this question starts now. There may be a possibility that you won't get the answer. Do not panic. I will give you the whole situation and plus the answer. Just think about it. What we have to do, right? You have to start the water with the liquid state, which is at 10 degrees Celsius, and then you have to move towards your ice, which is at minus 10 degrees Celsius. Now your time starts now. Just think about the situation, that what all the processes can be included in this process. Okay, your time is up. How will solve it? For those who solved it, the correct answer will be minus 7.15 kilojoule. Okay. Now what is given in the question? The enthalpy of fusion is given. So I have converted this thing into kilojoule from kilojoule to joule by multiplying it with a factor of 10 to the power 3. And the Cp for the liquid water is given. Then the Cp for the solid water, which is ice, is also given. Now what is the situation? There may be a case you won't be able to analyze the situation. So that is the part where you missed the question if you have not solved it. Now the situation says that you have to start from the water liquid. Okay. Then you have to move to 0 degrees Celsius with the water as liquid state. Now at 0 degrees Celsius, there will be a transition, phase transition from liquid water to ice. This temperature will be maintained, which is 0 degrees Celsius, until and unless whole of the water is converted from liquid to solid. Then next, once you got your solid ice at 0 degrees Celsius, then you have to take it at an even lower temperature, which is minus 10 degrees Celsius. So 3 processes are involved here, and you have to calculate the enthalpy change for each of this. Let us begin with the first part. The first is what? Starting from the water, liquid water, you have to start from the 10 degrees Celsius and bring it to 0 degrees Celsius. Then for this case, you can easily calculate your enthalpy change. Now we have calculated this enthalpy change in terms of heat, because in this kind of process, we always keep the pressure constant. Remember this thing. If you are keeping the pressure constant, then we can say that the enthalpy change will be equals to the Q, and this thing is being already mentioned in the phase transition discussion. So what we can write? N into Cp delta T. So that is the equation for the enthalpy change, right? Now N will be what here? It will be 1. Why I am saying it as 1? Because it is mentioned in the question. Next thing is the temperature change. So that will be 10 to 0. So 0 minus 10, which is minus 10 again. And what about the Cp? It is given in the question 75.3. We will take the Cp for the liquid case, because we are bringing the liquid situation from 10 to 0. This value will be minus 753 joule. What is the next situation that we will carry out? We will see the phase transition. Now for the phase transition, it's very simple. You just have to multiply with N. Why I am saying it? Because we already have the value for the fusion case, and it is for per mole. The only thing that we have done is converting the kilojoule to joule. Now your question arises, do we have to consider for mole? Yes, we have to consider, but the thing is already given in 1 mole, right? We have to calculate it for 1 mole. So we don't need to convert it. We have to multiply it with 1, and that will give you away the same result, which is 6030 joule. Is it clear till this part? Okay. Now, if this is clear, we have moved to two steps right now, from cooling from 10 to 0 and transitioning from liquid to solid. Then what is the next thing that we will see? We will see the temperature change of the solid state of water from 0 degrees Celsius to minus 10 degrees Celsius. So let's do it. How we'll do it? You will apply the same formula. The only thing that we will change is your Cp value and the temperature value, right? Moving on to the next step, which is conversion of, I would not say conversion, reduction of temperature from 0 degrees Celsius to minus 10 degrees Celsius for solid water or ice. We will apply the same formula, which is NCP dt. Here we will change the Cp value because this is for solid part. We will take it as 36.8. Now the temperature change is from 0 to minus 10, which will give you the delta Ts minus 10. Therefore, the correct value for the third step, or I would say the enthalpy change for the third step, would be minus 368 joule. Now, if these three parts are clear, we can calculate the total enthalpy change, which will be the summation of the previous one, Q1, Q2 and Q3. If you add all of this, you will get your total value as minus 7151 joule. Now, it would be appropriate to convert this joule into kilojoule. In most of the cases, in the textbooks also you will see it, and it's a standard one. For that, we are dividing it by 1000 because we have the conversion factor of 1 kilojoule is equals to 1000 joule. Finally, we can write that for the whole process, which is starting from 1 mole of water at 10 degrees Celsius, which is present as liquid state, you have to convert it into ice, which is at minus 10 degrees Celsius, and it is present as solid state. The enthalpy change will be minus 7.15 kilojoule per mole. Obviously, it is for per mole because it is given in the question. Now, moving on to the last question, which is for the reaction 2A plus B giving us 2D, you have to calculate the delta U naught. The delta G naught. Delta U naught is given minus 10.5 kilojoule and delta S naught is given, which is minus 44.1 joule per Kelvin. You have to calculate the delta G naught as well as look for the spontaneity, that whether the reaction is spontaneous or not. So your time starts now. So your time is up. Let's see what is the correct answer. So the delta G naught will be positive and the reaction will not occur spontaneously, because for the spontaneity condition we have negative value for delta G naught. Let's see how we are solving it. The given reaction is 2A plus B giving us 2D. You have to again use the equation of delta H naught and delta U naught to calculate the delta H naught, because the delta G naught requires two things: enthalpy change and inentropy change. Now, what is the given data? We have the internal energy change, which is minus 10.5 kilojoule, and we have the inentropy change, which is 44.1 joule per Kelvin. We are converting it into kilojoule because, as I have told you in the previous question also, to get your answer in a kilojoule part is a standard thing. The temperature is also mentioned. It is 298 Kelvin. And the gas constant is 8.314 into 10 to the power minus 3 kilojoule per Kelvin per mole. Now, why I am taking the temperature as 298 Kelvin? Why I have said that it is given? Because all of these values are at standard conditions. See, we have the not thing. So, we can calculate the change in moles of gas, first of all, to calculate the enthalpy change, which will be moles of gaseous products minus moles of gaseous reactant. The answer will be minus 1 mole, right? Next, what we will consider? We will consider it for the delta G calculation. So for that, we need the delta H naught and we already have the delta Ng. Now you can put this in the equation between the delta H naught and delta U naught. If you substitute the values, what you will get? You will get your delta H naught as minus 12.98. See, we have set up the value for the delta U naught as minus 10.5. We have taken delta Ng as minus 1. We have calculated this thing in the previous part. The value of R was also mentioned and T is 298, which is at standard condition. Now this will give you the total value of enthalpy change as minus 12.98 kilojoule. Next thing what we will do, we'll put this thing back in the Gibbs free energy change equation. So what is that equation? Delta G naught is equals to delta H naught minus T delta S naught. So this is your equation. If you will put these values here, what you will get? You will get your delta G naught as plus 0.16 kilojoule. See, we have calculated the delta H naught or the enthalpy change as minus 12.98, and we have also calculated the it is already given in the question, the entropy change, which is minus 44.1 joule per Kelvin, but we have converted this thing into kilojoule, and therefore the value is now minus 0.0441. After calculating this whole thing, you are getting your Gibbs free energy change in a positive term. Therefore, the reaction will be non-spontaneous at the standard condition of 298 Kelvin. So this was all for the exercise part. I hope you enjoyed the session. Thank you for attending it.